I'm going to talk about innovative approaches to the future management of heart failure, with the full realization it's very difficult to predict the future. But I'm going to just at least raise with you some speculative issues as to how maybe the future may turn out. I'm also going to focus on heart failure with systolic dysfunction. I'm not going to address at all the entity of HFpEF. So if you look at the evolution of therapy for heart failure in the present and more recent times, it's really been improving hemodynamics, and then that shifted towards neurohormonal inhibition with ACE, ARB, beta blockers, aldosterone antagonists, and we'll talk about LCZ 696. I think what's important to emphasize down here in terms of management is that we need to titrate the drugs to the maximum tolerated doses that were used in the trials, because we have a very good body of trials. Non-pharmacologic therapies, I put a question mark next to CPAP. I think it is going to play a role in heart failure. ICD, CRT, ventricular assist devices, and cardiac transplantation. And in this regard, there's been a lot of discussion about viability. Let me just point out that the STITCH trial, which was a very good and difficult trial to do, really the use of CRT and ICDs was way below what it is now, which again emphasizes that all trials become a little obsolete by the time they're published if they take a couple of years to complete. So the future, and what I'm going to concentrate on, is on unraveling the molecular genetic web, the identification of new therapeutic targets in the sarcomere, the signaling mechanisms, calcium transport, and energetics, the role of pharmacogenomic profiling, and then obviously I've put there with a big question mark, stem cells, gene therapy, advances in transplantation, the artificial heart, and long-term biomarker and hemodynamic monitoring. So these are the four areas I'm going to concentrate on, beginning right here with new pharmacologic approaches. Now, what is the rationale for the use of the natriuretic peptides to prevent LV remodeling? After all, BNP levels are already elevated in heart failure. So why are we spending time and money on trying to raise the BNP levels further? And the reason is this: that cardiomyocytes secrete large but unprocessed amounts of the poorly active prohormones, pro-ANP and pro-BNP, or fragments of the biologically active BNP I32. So the BNP we measure diagnostically is not the same BNP that we want to use therapeutically. So future approaches are going to focus on augmentation of atrial natriuretic peptides and BNP signaling, neprilysin inhibition, we already have that. The application of synthetic modified natriuretic peptides is going on right now, a lot of that work at Mayo Clinic. And this is an interesting approach, stimulation of the cardiac convertase that locally activates the NP prohormones and converts them into biologically active hormones. Well, you all know about the angiotensin neprilysin inhibition trial. What is interesting is this accompanying article from Dr. Brownwald that points out how long it takes to get there. It's a really beautifully written article that begins with the identification of the ACE gene, and it took about another 30 years. And I'll close with my favorite topic, which is stem cells, and with a plea, be patient, people, be patient, it takes time. Now, the concept of pharmacogenomic profiling for drug therapy in the treatment of heart failure has been around for some time, and I think of it as somewhat of a promissory note, but it's evolving. This is a dynamic and progressive field, and I think the impact of genome-wide screening and GWAS studies on pharmacogenomics and heart failure therapies will probably become a substantial reality, but it's taken time. This is with us, and we will only see more developments, wireless PA hemodynamic monitoring in chronic CHF. This is one technique, the cardio-MEM system, and in this study, a huge difference in cumulative heart failure-related hospitalizations. It's interesting to me working in a CCU. One of the major problems in heart failure is the very, very high readmission rate. And yet we keep people in our ICU for a year waiting for transplantation. And they do well. They do well. Their weight goes up, we give them a little diuretic, we watch them carefully. There must be a way to do this as an outpatient with wireless technology. And there's a lesson there. Because I think the readmission rate in the United States, 30 days, is somewhere around 30 to 40%. But these patients in the unit stay stable for a year. Why? Because we weigh them and we titrate our medications accordingly. So some wireless hemodynamic monitoring is just going to go from strength to strength. This article from Dr. Brownwald points out the complexity of the biomarker profiles. There are many, many biomarkers. The key is going to be what is the incremental amount of information provided. Not does a marker of stress or myocardial stretch or myocyte injury, not whether it correlates with prognosis, but does it correlate with prognosis over and above what we already know? And that's the challenge for the whole biomarker field. Now to go to the more complex area, unraveling the molecular web, the molecular mechanisms of contractile function, calcium signaling, myocardial energetics, and microRNAs. Now this is a very detailed diagram, and I show this from a review by Mudd and David Cass at Hopkins. This really illustrates the sort of elegance, the sophistication, and the incredible complexity of the cardiomyocyte signaling pathways that transduce stresses like catecholamines, free oxygen radical species, into the development of left ventricular hypertrophy and ultimately a myocyte function. It's an incredibly complex process. Now, in the next few slides, I don't want you to concentrate at all on the detail, but I just want to emphasize the sheer breadth of targets and interactions. If you look at this, calcineurin and NFAT, activation of a hypertrophic genetic program. These are mediators of left ventricular hypertrophy, PKD, MAPKs, and CAMK2. Here, GSK3 beta FOXO, negative modulations of LVH. And out here, PKG, multiple functions activation by PDE5 inhibitors. And then as we get down to the HDACs, we're now getting down the final common pathway, and activation of these has both protective and pathophysiological effects of cardiac remodeling, and then the microRNAs, which are regulators of gene transcription and translation. And they may play a critical role in hypertrophy, arrhythmogenesis, and calcium handling. And I think I'll come back to this in a moment, but this is an area of enormous interest because one microRNA can suppress anywhere from 20 to 200 genes. Now, calcium cycling in the normal heart, again, is a very complex process, and there are two real key aspects of it. The calcium uptake pump, the SR circuit calcium 2 pump, which is inhibited by phospholamban, which when phosphorylated, it activates the pump. And what this calcium pump does is really pump calcium into the sarcoplasmic reticulum, and it plays a fundamental role in relaxation, and maybe in HFpEF. The release of calcium through the cardiac ryanodine receptors of calcium into the cytoplasm governs contraction. And obviously this is a simplified diagram, but there are a number of factors that work on the calcium pump that are critical to excitation, contraction coupling. And this led to the CUPID trial, which was the first trial of gene therapy. The observation that a deficiency of an enzyme called sarcoplasmic reticulum calcium ATPase, or SERCA2A, is linked to the progression of heart failure, and that correcting this abnormality by gene transfer may improve cardiac function. Now, this led to the first CUPID-1 trial with an adenovirus directed at this, and it was a small trial that was positive. And then it led to the CUPID-2 trial, hasn't been published yet, but presented at ESC by Barry Greenberg, 250 patients with heart failure, primary events, recurrent events, and primary and secondary endpoints shown here. Unfortunately, it was completely neutral. Completely neutral. And does that mean Does that mean it's inadequate gene transfer? Is it the wrong dose? Is it the wrong agent? Is it the wrong target? And we're back to square one, but a very, very attractive target because circuit 2A really, in a way, is the key to excitation, contraction, coupling, and both contraction and relaxation. Let me come back here. So microRNAs are non-coding RNAs. Each one can repress 20 to 200 genes. What I think is important is that they can be antagonized by molecules called antagomeres. Here are two papers in Nature, and one of them, inhibition of microRNA 25, improves cardiac contractility in the failing heart. This is again in the future, but there's a lot of work going on with the microRNAs and a lot of interest. A new drug, omecamtiv mecarbil, is an interesting drug. It is a cardiac myosin activator. It's not an inotrope in the normal sense of the word. We learnt in the 1990s that inotropes kill people. They may improve ejection fraction, but they kill people through arrhythmias. This is not an inotrope. It prolongs systolic ejection time and function. Shown here in yellow is the drug. This is Cleland's trial published in The Lancet. And you see with administration of the drug, a large increase in systolic ejection time. The area in white is the administration of the drug, and you also see a large increase in stroke volume. I'm not sure why we haven't seen more of this. This is a positive trial in a small trial, an interesting drug, because it achieved all of this without changing the heart rate, and there was a reduction in LV end systolic volume and LV end diastolic volume. I'm not sure where we are with this. It was certainly a promising phase 1 trial. Now, this is really interesting work and emphasizes a number of points. First of all, I want to emphasize the difference between dilated cardiomyopathy and ischemic cardiomyopathy. Ischemic cardiomyopathy is characterized by scar and LV dysfunction. Dilated cardiomyopathy, a publication from my old university almost 20 years ago said, if you look at patients with dilated cardiomyopathy under the microscope, there's not much to see. A little edema, a little hypertrophy. With an MRI, very little scar tissue. And the point to be made is dilated cardiomyopathy is dysfunctioning myocardium. It's not scarred myocardium. It's a very different entity from ischemic cardiomyopathy. Now, the very first paper, I think, that drew attention to the genetics of dilated cardiomyopathy was from one of my colleagues at the Mayo Clinic, and it was an echo paper. But subsequently, Dr. Seidman's group have identified truncations of titin causing dilated cardiomyopathy. Now, this is very exciting for dilated cardiomyopathy, but there may be other implications of this. Robertson Ware at the Brompton in London recently showed that titin is the most common genetic cause of dilated cardiomyopathy in ambulant patients in the community. And the logical extension of this sort of work is, what is the role of titin trications in cardiac remodeling? And this is from the classic diagram of Mark Pfeffer showing an acute myocardial infarction, infarct extension, remodeling, dilatation, and chronic heart failure. And perhaps polymorphisms of titin may be involved in this process. And of course, if it is, this is going to tell us a great deal about whether we can modify heart failure in its developing phase. I think very interesting potential work. Surgical therapies, revascularization for ischemic cardiomyopathy. It's logical. The STITCH trial was modestly positive. Viability testing remains under evaluation. I believe the viability sub-study, and I know Haron Bax agrees with me, really was inconclusive. Revascularization plus the DOR procedure, surgical ventricular reconstruction, was of no benefit in the STITCH trial, but it still may be beneficial in those patients with classic LV aneurysms, which we don't see in the United States anymore with reperfusion. What about mitral valve repair with or without the core cap device shown here? The work from Michigan really has shown no mortality benefit from mitral valve repair in dilated cardiomyopathy. There is improved remodeling. The issue of mitral valve repair versus replacement is still subject of ongoing trials, both surgical and percutaneous. But my own opinion is, for what it's worth, and maybe Dr. Taggart will comment, surgery is most effective when it's directed at the cause of the problem and not the consequence. And functional mitral regurgitation is the consequence of ventricular dilatation. It's not the cause. But we'll get an answer to whether this is a useful approach from the ongoing COAP trial of MitraClip for functional mitral regurgitation. It may help symptomatically, but it won't change the disease. Destination in bridge therapies, I'll say something about this in the next slide. Ongoing evaluation and miniaturization likely to be employed earlier in heart failure. And cardiac transplantation. Limited donor supply, huge problem in the States. Xenotransplantation, ongoing animal investigation. The great late Norman Shumway, the cardiac surgeon from Stanford, said, xenotransplantation is the future and always will be. And I think he's right. I just don't see that, at least in our lifetimes, as being a solution. LVADs of today are much improved, but many problems still exist. What we are going to see in the future, smaller pumps, lower mortality, many LVADs that provide partial support and used in ambulatory heart failure will be more widely used. I think it's just fairly soon before many LVADs will be implanted in a cath lab or as part of a hybrid procedure, and then electrical transcutaneous stimulation to eliminate the need for a percutaneous driveline. LV assist devices, we use them as destination therapy, as a bridge to transplantation, but this is what's really interesting, the bridge to recovery from a scientific standpoint. It's a minority, but about, I think maybe 5 to 10% of patients who have had an LVAD implanted, the device has subsequently been explanted. It's all been in patients with dilated cardiomyopathy and not ischemic cardiomyopathy. But it's been explanted, and these patients appear to have improved, at least for a certain period of time. And why I think this is so fascinating is really we need to understand, again, the mechanics of the cellular, structural, and functional recovery, the predictors. How can we augment this? What are the molecular mechanisms? Who are these people that improve, and why does unloading result in whatever genetic upregulation there is that they can improve? So other than that this is an interesting clinical phenomenon, it's a wonderful animal or human model for scientific exploration. Perhaps the end-stage failing heart is not so end-stage after all, at least in some patients. This is another one of many concepts that are being proposed at the moment, is whether you can restore the shape of the LV by, in this case, Algicil is an interesting observation. And this study presented by Doug Mann, small but statistically significant improvements in functional capacity and heart failure symptoms at 12 months by placement of an alginate hydrogel, which stiffens the heart and prevents remodeling. And there are a number of mechanisms and devices that are currently under evaluation. So let's close with stem cells. And cardiac cell repair is a topic of great interest to me, but we really are at a crossroads. On one hand, is this the end of the beginning or the beginning of the end, as Winston Churchill said? And I made the mistake of speaking at a big stem cell meeting, and I got my words mixed up. And I said we're at the beginning of the end, which didn't go down well, since everybody in the audience, that was their career, was stem cells. I meant to say it was the end of the beginning. But here are the problems and the reasons for optimism. Causes for cautious optimism are, there's ongoing basic research on multiple fronts and in many countries. But somehow it's been lost in clinical translation. We haven't got our message across. But the progress and the scientific basis of knowledge of cell repair therapy is growing at a huge rate. Clinical trial results have shown safety, but the benefits have been modest. The trends have been in the right direction, and clinical trial design has improved. But here are the concerns. The benefits are modest, the trials are neutral, and maybe it was our fault in the stem cell community that the expectations of the public were completely unrealistic, and perhaps of physicians too. And now when you raise the expectations and you come out with neutral results, there's an overreaction. And there clearly has been, I think. In the scientific community in the United States, there are real concerns over the extent of stem cell research funding. The state of California, which is in a financial crisis, I think raised $2 to $3 billion under Arnold Schwarzenegger for stem cell research. If you go to Stanford, you look at every building, it's a stem cell research building. And I've said to them, what's going to happen if this doesn't work? And they said, well, we will change the name of the building. But in the scientific community, this is true. I mean, scientists are saying, well, you've had all the money, what have you come up with? And why doesn't some of it come to us? So this is something we need to address. And then I'm afraid there are legitimate concerns about scientific credibility. Some are justified. There have been some well-proven cases of scientific fraud that have hurt everybody. Some of the accusations are completely unjustified, including a recent British medical journal that I think was article that was totally irresponsible in terms of errors in some of the stem cell trials. The field of stem cell research is active, robust, international, and encompasses both bench and bedside. I don't expect you to read in detail, but there are at least 39 trials ongoing in ischemic and non-ischemic cardiomyopathy, phases 1, 2, and 3. I'm a PI of one of the trials, as is William Wines in Europe, on a particular stem cell that has been developed at the Mayo Clinic called the guided stem cell. The different cell sources, different cell types, and different methods of delivery, all the subject of ongoing trials. My conclusions are that allogeneic cells are likely to be the predominant cell type. You see, when we take cells from a patient's bone marrow, we're taking sick cells from a sick patient and transplanting them back. We're going to have to take cells and grow them from healthy patients. Evidence for the paracrine hypothesis is strengthening. It is not that these cells replicate and become myocytes, but they elaborate other substances that are beneficial. It may be that in the end we will grow the cells, and what we'll administer to the patient are not cells, but the supernatant, or whatever it is that the cells elaborate. Blinding is essential. We learned that with Simplicity Hypertension 3. It's essential in these trials. We have to have a sham procedure. But make no mistake, if we had a pivotal trial that demonstrated a 10% change in ejection fraction, it will change clinical practice. Do you know what the change in ejection fraction was with streptokinase in the GC1 trial? 2%. So we'll see. Resident cardiac stem cells, as developed by Dr. Marban, and guided mesenchymal stem cells, as developed at the Mayo Clinic, are promising. We need larger trials, and we're also going to have to focus on strategies, not just the cell, but ways of making the environment, the cardiac environment, less hostile to the cell so that they can survive and proliferate. My last slide is this, and it brings us back to earth. A very nice study of 5,000 patients and the contribution of major lifestyle risk factors for incident heart failure in older adults. The independent predictors of reduced incident heart failure in the cardiovascular health study were physical activity, modest alcohol intake, BMI less than 30, non-smoker. Interestingly enough, dietary patterns didn't matter, providing the BMI was within normal limits and the patient was a non-smoker. And shown here are the number of lifestyle risk factors and the number and the percentage of participants and the number of lifestyle risk factors that were modified. And what you can see is a very, very striking reduction in the incidence of heart failure according to the number of risk factors that have been modified. So that brings me back to really what Dr. Ferrari said, prevention is the key. One of our great presidents, it is common sense to make a method and try it. If it fails, admit it frankly and try another, but above all, try something. And I think we're in a very active and interesting field, but there will be many disappointments down the road, and we have to be patient. Thank you for your attention.